Alright, good evening and welcome everybody to N Simplex Pachinko. This is Obi-Wan Pez. And tonight we are mostly going to be just kind of messing around with whatever anybody else wants to talk about. I don't have anything in particular to like really set out to do, but can do just about anything. Sorry. Messing around with stuff that I should have messed around with a long time ago. Mr. Bobbin... Bobbin Sonics. Yes, so this is a Colat's map that I started doing on the whiteboard here just a little while ago. And I've got actually a much more complete one right here, which again, I don't want to say complete, but you know, it's got at least a few more branches that are going off to this whole side and then off that way up to the corner of the page. That was just something I was messing around with, like, you know, this is basically my version of doodling. Um, so every so often I just come back and start making a couple more branches or expand something. Sorry. You know, the easy stuff was taking any one of these branches, finding a finding a value that branches off, and then just keep doubling until I feel like stopping. So that is one of the easy things to do. So I did notice a couple of random patterns in here. I mean, clearly not random, but a couple of interesting patterns. We had branch every time that x mod 3 was equivalent to 1 if x minus 1 over 3 was an odd number. So you get 64, 16, technically 4, but that's a little boring, 256, 1024, etc. So all of these are going to have a blue branch coming off of it, and then it's just going to keep doubling off, and then we'll eventually start filling in like where each of these individual ones will, well, not all of them, but some of them will eventually branch off to create their own. So, welcome to it. How you been? Is there anything in particular I can help you with tonight, or at least give it an old college try, if you will? Yes. Well, we will eventually find them all, I'm sure. At least locally, anyway. This is the other thing, is that if you can find a place where they branch, so like here we found that 4, 16, 64, 256, and 1024 are all going to branch. This is going to be every other value is now going to branch infinitely along this entire, well, trunk, I guess. Like the powers of 2 are going to be considered the trunk of this tree. Then coming off of here, once we have the 5, found that 10 is going to be a number that's received by 3. And so from there, again, every other is going to branch to create its own. It turned out, like, at some point, I had done this, and I was a little more reckless about, like, what I was doing. And I think 20... no, not 20. There's some number in here, I don't remember where the even number would branch, or the number would branch to an even number. And I think it was an odd, right? Must have been. Yeah, right. The 21 won't. I think that must be it. Is like somewhere in here. No, these are all multiples of 3, right? Because it's x mod 3 has to be equivalent to 1. So here x mod 3 is 0. So that's never going to work. But this one, yeah, this one's equivalent to 1, so it's going to have branches coming off. But at some point, it was like a number like 83, for example, was going to come out to... No, it's not 83, though. Damn. I don't remember where it is now. There's some number, anyway, that you look at it, and it's... The value is 1... Oh, is it 13? Yeah, because if you take 13 and you try to walk it back, right? So you take x minus 1 is going to be 12 over 3 is 4. So this would come back and say, oh, look, 4 would go to 13. But it doesn't because 4 is even, so you'd have it. So I was a bit reckless in where I was grabbing some new numbers. So I said, oh, okay, 4 is going to triple and plus 1, and then you can get 13. And then I did like a whole branch with 4 on it, and then I was like, wait a second. That doesn't work. Curses. No. So yeah, there was a 7. Yep. So you have to find, first of all, the numbers have to be even, right, in order to... Well, that's a very good question. So, where's 7? 7 would have come from 14, which itself would have either come from 28, 56, and 112, or these are 28 would have, yeah, okay, 28 would have branched from 9. Which would have come from 18, 36, and these are all multiples of 3. So, good question, right? Where does this go? If we continue down, that can triple 7 to 21, add 1 to 22, becomes 11. We'll find where it comes from eventually, but I don't see it yet. 33 plus 1 is 34. 17. Triple is 51 plus 1 is 52. 26. 13. 26. Yep, got it right here. So 17 would be a branch, side branch off of 52. Gaussian integers and an additional rule for mapping complex component. Goodness. Was that what we were talking about last week? Maybe not. So one of the problems with me in particular is that I'm not super well versed in a lot of mathematics outside of... No, I know. Sorry, I thought you were like looking at our video on demand or something like that. Anyway, I'm not actually super well versed in a lot of upper level mathematics. Like what I've done for my master's was the most recent stuff that I delved into. Most of that was partial and nonlinear differential equations, and that was 11 years ago. So most of it is like gone, which is too bad. But sometimes Super Brain here gets me onto something, and we start talking about all sorts of cool stuff. Kind of depends on what the inspiration of the week is. So yeah, last week we did Pette approximants and Gaussian, no, Lagrange? Yeah, Lagrange interpretation. Well, the other thing is that I also skipped a lot of the undergrad mathematics because I did math education. And so like I didn't get to do that until uh, until the master's program was like, you need to go back and do a bunch of these things. So fill in the blanks here. And so some of them were like real and complex analysis I did as part of my master's, whereas my spouse did that as part of her undergrad. So uh, she was a tremendous help on on a lot of that stuff. It's doing it again. And it's keeping the black pen on even though I selected red, but it doesn't actually show. It's just sprite stuck. Um, nice. Yep. So I never had that distinction. I kind of wished I did at some point. You know, it definitely would have helped me. I ended up taking, what was it? The um, senior level linear algebra at the same time as one of my math education classes, and maybe another math class, but yeah, I ended up spreading out a lot of my stuff, so I had a decent number, kind of scattered throughout. Yeah, God, I love him. He's so great. Yeah, black pen, red pen is a often on my playlist at school. Um, so anyway, we'll stop with the mandala-ing here and move out to a new whiteboard. Yeah, I was doing a little tiny bit of work with cat and mouse graph theory problem. Heard of it? Yes, I think. I'm imagining you're doing some work with Gaussian integers on that one, or is that not connected to above? Oh, graph theory, I guess, so it doesn't necessarily have to do with 2D plots. Yeah, go ahead and describe it, and I'll that's not what I meant to do. Okay. Okay. Interesting. So if we just like, is it a complete? I forget the terminology now, but is it like everything connected with everything, or is it just like random? you know, whatever connections are here are just here. Any graph? Okay. I mean, yeah, so I guess there would be a bit of a problem if there were superposition. Alright, so then somebody comes along and erases, like, this connection, and then... Oh, yeah. So somebody comes along, erases that connection, and then the cat moves off to this one here, and then the player, strategy-wise, would probably eliminate this connection to trap the cat over here. And the cat would try to move, if this was a thinking cat, probably move into a larger space, which again, the strategizing player would eliminate this connection. And then the cat would move, yeah, wherever. So I mean, basically you're just, I don't know if it's always true, but either you eliminate the, if the cat is moved into a location that has fewer connections than where it was, it seems that the optimal strategy would be to remove the place that he just crossed, right? So take out the, so either one or two remove a connection that, how do I want to say this? I have it in my head, but like that eliminates the most nodes, something like that. I mean, it happened to be that wherever the cat was, that was where I was just eliminating, but it doesn't necessarily mean that that's the optimal procedure. So, Angels dancing on the head of a pin? No, I don't know that one. I don't think I know the angel problem then. Well, yes, but so if the cat did just go back the way it came, it did waste a turn, but at the same time, that could be the optimal strategy for it to survive the longest. You know, survive. Surely you want angle problem. No, no. Oh, it's a Conway game, of course. Uh, oh, okay. I see. So it can jump to anywhere you want, anywhere it wants. So I think the optimal cat strategy would be to move to the place with the most interconnected nodes. With the fewest connections of one only, like single nodes. Maybe. And then the optimal player strategy would be to whittle down, try to get the cat cornered by eliminating so really, I mean, it's just eliminate the connection that eliminates the most nodes. I mean, really, it's not cat and mouse. It's more like cat is mouse. Yeah, so at our house, we used to call this taking the cat to the vet. Was more or less how this works. Try to corner the cat as best you can and put her in the box. So, yeah. So I mean, if you can't, if it's not going to be quick, if it's a like a complete graph that has every literal connection uh, present that exists, then yeah, you're going to have a fun time with that one. So I think it's just going to be like start eliminating some. Because as soon as you start eliminating ones that the cat is attached to, then they're probably going to shift to a different one. Try to go to the most interconnected region after that. So it seems like you're just going to have to like have it, and then have it again, and then have it again as best you can. So yeah, I think that's going to take... So yeah, I think that if you ended up with a complete graph, I'm not going to do them all, obviously, but So if all of them are interconnected 100%, I think that if the cat is going to be here, you just have to basically say, okay, 1, 2, 3, 4, 1, 2, 3, 4, and chop all the connections that cross this line. And, or choose where the cat is and say, I'm going to chop all the connections that are not connected to the cat at all, so the cat won't move in theory. Basically, you like chop all the connections that cross this line. So if you slice all the connections that cross this line, you end up with two distinct regions. Well, I mean, yes, but that might be the only way to go if the cat has free movement anywhere. Because the second you cut one connection that the cat has here, it's just going to jump to another node that has all connections to everywhere else. And I mean, a complete graph is ridiculously connected anyway. Yeah, okay. So if the cat's here, right, you cut this one, the cat's going to move over there, which is equivalent to you cutting this one. So, I mean, that's kind of trivial, but... and then you can cut either and it brings it back down. Okay, so you get this one, cat's here. If you cut any of these three, the cat's going to move to the opposite node. Well, not necessarily the opposite, but one of the other two that still have all three intact, which is again equivalent to you just cutting this connection here. Oh, I'm sure. Oh, so literally I just did. I cut the one that was crossing the diagonal. Right, so like what is going to cut this graph as efficiently as possible? I think that right now we'd have to say okay, so if we cut this one, right? Again, if we cut any of the ones that the cat is attached to, then it just runs to a different place and it becomes equivalent to what I just did, right? Cutting the diagonal that's opposite the cat. Or one that doesn't connect the cat to anything. So the cat stays in a location that still has three connections, whichever one that is. Right. So if we do that, in order to cut it into two equal pieces, right? If we cut one of these three, again, cat's going to try to jump to either this one or one of these other two that have now two connections. Or possibly three, depending on what's here. Cats are most definitely a second hostile player in these sorts of events. Right, so if we cut this one, then we still have three connections here, so the cat's going to jump there. Probably. Right, because cutting any one of these is going to potentially make the cat run off to some other place. So again, this would be equivalent to saying, okay, we're only going to cut either. We can cut the diagonal, but I wouldn't like that so much, because that'll just make them all equivalent again. And if we eliminate one or either of these, this is just going to separate it out into a carbon atom, basically. No. Nope, I'm wrong. Boron. Right, where it's connected to the three things that it's attached to, but... sorry, CH3. I'm getting distracted. Anyway. So we can cut this middle one, which then makes it a square. So 1 would bring it to a square, 2 would bring it to a line. So that'd be potentially helpful. One, 2 would take it to one of these with the cat at the center. And then cutting one more would make it into a line of 3. Or you could go 1, 2, 3, 4 with the cat at one of the center points. Right, so this is what we ended up with. This one would be faster, because now you can chop this point, and then now it's down to 2. If you, because if you did one of these, now you're down to 3, so you're only eliminating a side one. Right, so this is the worst case scenario, is that the cat's in the middle, in the one of the two middle spots, in which case you can eliminate 2 and get it down to 2. The worst case here is that we're down to 4, but you can only eliminate 1 at a time. So yeah, line's better. So then we want to, nope. So then from this graph, that was eliminating the other diagonal, making a square, and then eliminating any one that it's not connected to, so either here or there. So it's going to be 1, 2, 3, 4, 5 moves is going to get trapped if we're on a complete 4. If we're on a complete 3, you need 2. So that's just... Whoa. I don't know what that was. Apparently I pasted something in. Oh, that was my... yeah, that was my Discord copy-paste that I was doing. Yeah. That'd be a good one. Hey, let me, you thinking on Twitch? Interesting. I I clicked on your name and it brought up a thing with a flag on it, and I was like, haven't seen that before because it has a new tag next to it. It says manage suspicious user. No, I don't want that. Um, yeah, we had somebody coming in here last time looking to sell something. I was like, no. Mm-mm. Woo! Thank you very much for the follow. Is it Bobbin Sonogs? Boop. Bobbins on OGS. Thank you. That makes much more sense. Okay. So yeah, if we go with this, we got 2 moves on a 3 3. It's called a complete graph, right? Yeah, okay. KN. Okay. It's been a very long time since I did combinatorics. That was about 12 years. So, let's see. So we go like this. We go 2 moves for case of 3, 5 moves for case of 4. I imagine this is going to start taking off probably exponential or much worse. Possibly factorial. Okay, so if we put cat at this node, again, let's do the thing that I was saying. This method is going to say we need to cut 1, 2, 3, 4 nodes here, or 4 connections here. So we'll cut 1, 2, 3, 4 first. Okay, we can make it a line then if we just go 4, 5, 6. Oh no, 6. That one's already cut. So if we cut the middle, we'd have to cut the entire middle out. That's wasteful. Hang on. All right, let's think. So 1, 2, 3, 4. Cutting all the ones that cross the center line. This reduces the graph that we have. That's silly. Outer ring. Except not that one. And then also this one to these 2. Right, but we don't need to, I don't think. So if we cut, at this point, if we cut, okay, so yes, it is, in theory. If we cut this one, right, then this brings us down to 2 on this side and a triangle, so a K3 on this side, so it reduces it to, not yet, but reduces it to something simpler. Right, and eliminating this one versus that one is equivalent. Eliminating this one is unnecessary, because if we can eliminate both of these two, the cat's going to avoid this corner as much as possible. So it might run into here, but it's still equivalent at this exact time. Okay, give me 1 sec. Alright, so is it necessary that we cut through all the ones through the middle in order to block off these things? It seems somewhat reasonable, maybe? Because we're cutting off all escapes. We don't want the cat to run off into one of the alcoves. So that's 4, 5, 6. And then this is now a 2-move 7, 8. So we can get it down to 8 moves for K5, but there might be a more efficient way. I just don't know it yet. So yeah, trying to like eliminate all the trying to eliminate all the possibilities where get it down to eventually a triangle. Doesn't have to be a K4. K3 would be more efficient, provided it doesn't run into some other random place. Cut off something so that it becomes a line, and that is a dangerous place for the cat to move, so it doesn't want to go there. It's too fast, right? We'll catch it too quickly. There we go. So if the cat is here, to the n-2, possible. I mean, oh, so actually we may have, this may be off then, right? That may be only 4. What time is it your way? 3? Misahide? Hi, how's it going? Almost 4. Oh, man. You don't need to get up on my account. But thank you for coming. I appreciate it. Okay, so what we want to do, really, that's fair. First is to eliminate one connection that exists between all other nodes so that the cat is enticed to stay where it is. So if we say, all right, that's going to be like this one here and this one here, so that all other nodes only have 4 connections, whereas the one it's on still, oops, sorry. No, all the other ones have 3. That's what I meant. All the other ones have 3, except the one it's on, which still has all 4. Right, so that's more enticing to stay there. Yes, so we had Mr. Bobbins on OGS came through and said, wanted to know something about the cat problem, where you have like some random graph that's just drawn, and what's the quickest way to trap the cat onto one single location. So you and the cat take turns. The cat will run to the most interconnected region that still exists, and then the player removes one connection that eliminates. Here, I decided the optimal strategy is the one that eliminates the most nodes. At the beginning, though, it may not eliminate any, so we're trying to figure out how this is all working. So I decided, very brilliantly, let's go and do a complete graph. So we're looking at how many moves the complete graphs take to trap the cat. So here, I said, let's eliminate one connection from each of the other nodes that exist. So the cat is still enticed to stay on this thing. We would like as much as possible to make either a single ring or eventually a line, because then you can trap the cat on a line. Currently we're doing a K5 complete graph, so but the idea is that it can be, I mean, literally it can be done on any. My hypothesis is that if you just like draw a line down the middle of the graph and cut it into like half of the nodes on one side, half of the nodes on the other, then the cat is going to just stay where it is. And as long as you don't eliminate the connections that connect where it is now, it'll stay where it is. This may be a wasteful strategy, but we're trying to figure something out anyway. Yeah, right. So you won't have to do any of this stuff that we're messing around with right now. So yeah, I mean, it looks like my theory might be correct, but at the same time, so if we eliminate like this connection here, okay, so I'm tempted to just say like I'm right, and we eliminate this one here and this one here, and then we make a ring, which then again we can start trimming down, and say like we do that one, and then this starts making, oh no, because that looks more like the tree. So we actually do want it to be So we want to trim out the middle ones first. So, I mean, the way that I would think to do it is to go 1, 2, 3 like this. This would then split it up into 2 triangles, which then you have a connection across the top, and we can cut that connection last. So then that would be similar to what I drew here, where you're just saying, okay, here's a line that cuts all the nodes in half, you know, half the nodes on one side, half the nodes on the other, and then let's divide them up. But again, that's my personal bias because I'm just saying I'm right. 1, 2, 3, 4. So that's 4 connections, which splits it up into 2 separate triangles. Okay. If we do that, then at minimum, okay, yep, and then we can cut up the middle again. So this would be 4, 5. This is when we start cutting here. It still has 3 connections, which is the most out of any of them. 6, which now gets it on a line. 7, it would jump to here. 8, 9. Okay. So yeah, it would be better, more optimal strategy to say that now we're on a line. No, don't make it a line. Eliminate 1 triangle first. Yeah. 3, 4, 5, 6, and 7, 8. Yeah. Yeah. So we found a better way to do it with 8 if you eliminate it down to 2 triangles. Can we do better? So 1, 2, 6, 7. Oh. I know, because that's never mind. Oh, 3. Yep. Because you have to literally cut every node or every connection. Right. And if you cut a connection that it's connected to, it's just going to jump to another one and make this equivalent. And then we have to do 1, 2, 3. Yeah. So we have to eliminate all 3. Okay. So 3, 5. It'd be nice if that was 7, but I don't think that's the case. Oh no, is it Fibonacci? Can't be that easy, right? 22. No, that's just 1. But it doesn't have to be, right? We found a slightly more optimal way, which is 9, or which is 8. No, I said Fibonacci, not Cromanici. So if you want to take it to a line, then yes, you can say it has to be 9. So if we do 1, 2, 3, 4, right? That reduces to a triangle and a triangle. So that's 4 cuts. Unless I did something wrong, which is always possible. Oh, which was... Gotcha. Yeah. Okay. A. Right, because if you cut the one it's on, it's going to jump over to the one you didn't cut, and then it's going to take 2 more. So it has to be 3 cuts for that. Okay. All right. 1, 3, 5, 9. 1, 2, 3, 4, 5, 6. So yeah, this is going to be more optimal. Allegedly. All right. Anyway. And again, I don't think there's another more efficient way, but could happen. Take out. Take out these 2 first. And one of these. All right, is there anything else? 1, 2, 3. 1, 2. 1, 2, 3. 1, 2, 3. 1, 2, 3. So it's cat would be just as likely to stay here as anywhere else. Allegedly. So where would be the best cut at this point? 1, 2, 3. Off of one of the other 3s. going to be that one? I don't know that we even need to disconnect here. If we disconnect this one or any of these three, the cat's going to jump to one of the others that does have three. So I'm wondering if we can trap the cat on this triangle here. So 1, 2, 3. That'd be like 4, 5, 6, and then 7, 8, 9. I'll get the K3. Yeah. Anyway, Mr. Bobbins, have a good night. See you around. Welcome in, and anytime you want, I'm here on Wednesdays for math streaming and Fridays for just fun, and we can always chat math, but most of the time I'm playing games or something like that, so. Alrighty, see you around. Alrighty, no problem. Alright, so 1, 2, 3. Yeah, and I'm not coming up with any fewer, but doesn't mean it doesn't exist, right? Evasion game on a graph from archive. That seems about right. Approximating the position of a hidden agent, that's something else. Although that's pretty similar. Cat and mouse game on an undirected graph, played by 2 players, alternating turns. Ah. Nope. Yeah, I came up with a few and more. Alright, so I found a coding site that asked for cat and mouse game for people to like program it, but not quite the same. It's a very low hum going through the house. I don't know what that was. Possibly construction. Evasion game on a graph. John Hasselgrave, 2018. Well, I mean, it's not 4 in the morning here. Yeah, it's only 10 o'clock, but yeah, we have a highway somewhat nearby, so they do have construction at night sometimes. Although I haven't seen any construction lately, so uh, but yeah, they do have first shift construction sometimes. That's pretty rough. Or third shift, whatever it is. Consider a connected graph to represent a network of mouse holes connected by passageways. Cat tries to catch a mouse by inserting a paw into one of the holes. If the cat has chosen the correct hole, the mouse is caught. After each unsuccessful attempt, the mouse moves from the hole it is currently in to any adjacent hole. Rudimentary form of this problem, asking how many cat. Yeah, so we we didn't actually do that, and we said that there was. Yeah, so that's not the same one. All right. Anyway. So yeah, this appears to, at the very least, be the pattern we're going to start with. So 1359. What about 6? Hooray! So if, big if, alright, so we'd have to, like, in theory again, sever all connections between them without the cat noticing first. Like 1, 2, 3, 4, 5. Alright, so now the cat is at the most connected node. So that's 5. 6. So then this is a triangle over here. Yeah, just be 7, 8, 9 going across like that. Which would then split this into a connected triangle and a connected triangle. And then 3 more would make that 12. In theory. It'd also be kind of nice if this was like... No. Never mind. I was gonna say if this was something like, you know, 2n plus 1 or 2n minus 1, but it's no. It's just not fitting. This is a weird, really weird sequence. What about evens versus odds, right? So 2, 1, 4, 5, 6, 12. Right, 1, 0, 3, 3, 5, 9. Hmm. This is gonna get so unwieldy. Stwix, welcome. Good evening. Absolutely. So if you have anything in particular, you can feel free to interrupt me because Superbrain and I are just playing around with a number theory or graph theory problem that another one of our viewers came in with, um, and has since gone to bed. So we're going to be kicking around with this for a while, I'm sure, because it's just a fun puzzle. Three, four, five, six. One, two, three, 4, 5. Oh. Which one did I forget? Ah, yeah, the one next to it. A. Alright, K7. So again, if we try to cut this way. Alrighty. X and Y intercepts of a quadratic equation. Yep. Okay. So, quadratic equations, or quadratic functions just in general, are going to generically be something, roughly speaking, like this. So, whatever equation you want to make up to go in here, I'm just going to make up a new one. So like 2x squared minus 15x plus, well, actually that's going to be a minus. And that's going to be a plus 15x minus 4. Let's go with that. So, when you're looking at an equation like this, typically you've got nice integer coefficients out front, so like 2, 15, 4. It's pretty good. When you're looking for the x-intercepts, you're saying here, this is where our graph crosses the x-axis. So when it crosses the x-axis, you can think, what is always the same? So no matter where it crosses the x-axis, we've got any given point along the entire axis is going to look like a. I shouldn't do a, sorry. Some n, comma 0, right? Our y value is always 0 on that line. And in fact, the y-axis, or no, the x-axis, sorry, has an equation, y equals 0. So you're trying to find the intersection between y equals 0 and y equals your equation. So this is going to take your equation from above and y equals 0 and couple these together. And the shorthand that we usually do is we say, okay, let y be equal to 0. And so 0 equals 2x squared plus 15x minus 4. There are two potential ways to solve a number of these problems. We'll go over both of them here. One for nice numbers and one for not so nice numbers. Really quick, because the other one is really quick. For the y-intercepts, y-intercept, you're looking for a single point which is going to cross the y-axis. And here again, let's give myself a little bit of room here. The y-intercept is, again, going to be where we cross our y-axis. And again, for every point that exists along the y-axis, we have a common thread for this. And that is that, again, the equation of the line is x equals 0. Every x value is 0. So we go on here and we say that this is going to be 0, comma, m. Right, just make up some number. Doesn't matter what it is. That's algebra for you. All right, then we go to our equation, and we do the same thing as we did over here, where we couple the x equals 0 part with the y equals 2x squared plus 15x minus 4 part. When we couple these, this says that y is equal to 2 times 0 squared plus 15 times 0 minus 4. This is the far easier one to do, right? If you ever want to find what the x-intercept is, especially in this form, right? When you have an expanded polynomial, it literally is just the constant part. So we have here 2 times 0 squared is just 0. Plus 15 times 0 is 0. Minus 4. So y equals that, which means that y equals negative 4 when x equals 0. These now become a coupled piece of information. When x is 0, y equals negative 4. So this is an ordered pair. 0, comma, negative 4 for our x and y values. So this is our y-intercept. All right. Now, let's separate these. To get our x-intercept or intercepts, because there could potentially be more than one. Typically, I will put parentheses around the s, because you can come up with a few different possible ones. Right. So the fun part about this is if you have multiple y-intercepts, right? How did it get both here and here? The answer is if it's a function, it can't do that. So this being y equals something, we can only get one possible value for each x value that we plug in. Okay. So for this part, we say, all right, there are a few different ways to get it. One is that we have a formula for this. So uh, we could just jump in and say, let's do it. Um, if you know the formula, great. If you don't, we'll get there. So the quadratic formula states that x is going to be equal to negative b plus or minus square root of b squared minus 4ac all divided by 2a. Now, yes, this is the boring way. This is the memorization way, which nobody really likes. So your a, your b, your c all come from this stuff here. Again, a is 2, b is 15, and c is negative 4. It is helpful to note that. Remember that you want to make sure you get the right positives and negatives in the right places. I will prefer making a positive every single time. Reason being, it's much easier to do all the other methods. It doesn't have to go that way, but it makes it a lot easier. Okay, so x is equal to negative b is 15 plus or minus. Sorry, let's move that because that's gonna. Okay. Plus or minus square root of 15 squared minus 4. A is 2. C is negative 4. All over twice 2. Okay. Then this becomes negative 15 plus or minus square root of 225 is 15 squared, plus 4 times 4 is 16 times 2 is 32. Aw, that's too bad. All over 4. Alright, this is equal to negative 15 plus or minus the square root of 257 all over 4. 257. Yep. I'm not seeing anything nice coming out of here, which really isn't surprising given the fact that I just made this up on the spot. So, this is going to be what we get for our x values. There are 2 of them. And the nope, that's behind me. There we go. The x-intercepts are then going to be negative 15 plus square root 257 all over 4, comma 0, and negative 15 minus root 257. This is kind of sloppy, sorry. All over 4, comma 0. I'm like right on the edge of my desk, so it's not helpful. And then my hand is also like on the edge of the tablet, so that's also not helpful. Alright, so we got our x-intercepts here in point form, right, as coordinate pairs, which tell us the location of these things. So it turned out that it wasn't, yeah, it's sort of like this, give or take. Okay, so this is method 1, right, quadratic formula for x-intercepts. Let's do blue here. Absolutely. So, method 1 is going to be formula. Now, I will say this one in particular doesn't factor, right? Just because we got some really nasty stuff. All right, so then method 2 is going to be factorization. Separate those out. And let's separate those out. All right. So, are you good with just regular trinomial factoring, like y equals x squared minus 5x plus 6. Like, you good with that? I'm going to explain it on the way to doing something else, but okay, cool. So if we look at this, the way that I recognize this, and again, this is a generalized look at this. So this is going to say that this works in every case that it does factor, no matter what. So what I do is I look at the a value that is here. In this case, again, it's just 1. And the c value here, which is 6. Now there's a slightly more rigorous way to look at this. What class are you in and what level is it? So if it's like Algebra 2 Honors, then, you know, you might be able to handle this. If it's like, you know, a developmental class in college level, yeah, maybe I don't want to do that to you. You also don't have to say that, but... All right, so the basic idea here with all of the factoring is we're trying to get this thing to look like m times x plus p times n times x, okay, n times x plus q. Right, we're trying to get this thing to look roughly like this. So I guess, is that okay? If this doesn't give you stress, then we're doing okay. All right, if we were to try to multiply all this stuff out, again, it's a little crazy, but it'll work. What we get that was nasty. All right, so here we get an m times x times n times x, so rearrange them, m n x squared. Over here, this is just an organizational method, by the way. Here we would get an np times x. Here we would get an mq times x, and here we would get a pq. So the way that a normal trinomial actually would be factored, or a factorable trinomial would look if you actually multiplied it out, would be this mn x squared plus these two things would add together because they have the same unit, x. So mq plus np parentheses x plus pq. Now, I'm not suggesting that you formalize this and try to do it every single time you go through. No, this is just to give you an illustration of how this all works. So when we factor this thing, regardless of what it actually looks like, if it is factorable, what's going to happen is that the factors from the first two positions, right, m and n, the things that are in front of x, will multiply together to get us a, right? So mn is equal to our a value that we're used to. mq plus np is going to be our b value. And pq is going to be our c value. Now, notice that inside of b, we have all four numbers. M, Q, N, P, or M, N, P, Q, however you want to look at it. Excuse me. And if we found the product of those two numbers, MQ and NP, right? Find the product of them. That's all four numbers multiplied together, MNPQ. And if we multiply A times C, that's MNPQ. So what we want to do here is say, what is MNPQ? In other words, what's A times C? In the above example, this gets a 6. And then we say from 6, we want all of the different possibilities to get us MN and PQ. What are the two factors? So the one we started from was 1 and 6. And then we also have the possibility of 2 times 3. Now, with many other numbers, there are many more factors in the list, so we can make it as big as we want. It's really good exercise if you have the time. If you have the time, try and find all of the factors for any given number. So when you come up with an A times a C, multiply them together, and then find all of the factors in the entire list. It's a really great exercise, again, if you have time. So then we want to say, which one reflects B? Which one reflects this MQ times NP? So is it 1 and 6, or is it 2 and 3? So here's the way that I worked it out. What you want to do is you want to look at first, the stuff that gets you B is a sum of two numbers, right? It's the sum of these two numbers here, whichever pair it actually is. The sum of these two numbers has to get you a negative value, which means, right, if you have two numbers and you add them together, two different stacks. Let's suppose that this is money, right? You have a bill that you need to pay, so that's a negative amount of money, and you have a check coming in, that's a positive amount of money. So then this right here, the -5, is our net income. We have lost $5 in total. So what does that mean about the money coming in versus the money going out? It must have been that the money going out was bigger than the money coming in. The bill was bigger than the check. So here, this tells us that the sign of the larger number is negative. So then we can go down our whole factor list and say, okay, the sign of the larger number is negative. Right? And again, no matter how big this list is, the sign of the larger number must be negative. Now you say, all right, what about A times C? Well, A times C got us a positive value, 1 times 6. Again, I want A, just for me, I want A to be positive. It doesn't always work that way, but you can always just factor out a negative from everything and then say, okay, A is positive now. So if A is positive, A times C is going to tell us that here we have either two numbers that are being multiplied together, which get us a positive value, or two numbers that multiply together to get us a negative value. In this particular case, they have to multiply to +6. So the only way for that to happen here is if the smaller number has the same sign as the larger. And this is, again, independent of what we found out about the middle number, or what we found out about the larger number. If this was positive, I could still make the same claim, that since the product of A and C is positive, this must have had the same sign as the other one. So in this particular case, we say it has the same sign, therefore the smaller one must also be negative. Now we look at this and we say, okay, based on this, which of these pairs adds up to -5? Well, there's only one. -2, -3. Now, resist the temptation to just jump to the factored form, which is, again, here. Right? Because I'm going to show you, again, the generalized method that works for any A value, not just A equals 1. A equals 1, we can say, okay, P is -2, Q is -3, and it's a shortcut. you can do that, but again, you don't want to do that if you're trying to, like, prove to yourself how this works. So what you should do, as a good habit, is say at this point, we got y equals, this is 1x squared. The middle term is what we just found, right? The -2 and the -3 were mq and np. So this is a -2 distribute the x. So an x squared minus 2x minus 3x plus 6 at the end. Keep everything else the same. Split the middle term into two groups. So again, here this is the -2 comes down as -2x. The -3 comes down as -3x. Then we look at this and say, okay, based on this, can we factor stuff in the first two terms and stuff in the last two terms such that we end up with a common factor? So the first step is doing a common factor factorization. So here we have a common factor between x squared and minus 2x, which is just x. The leftovers from x squared is going to be x, and the leftovers from -2x is going to be minus 2. In the second group, we have a minus 3x plus 6. We're going to bring this sign down and factor it out. As a negative, common factor between 3 and 6 is 3. When we take a -3 out of -3x, we're left with just x. When we take a -3 out of 6, we're left with 2, just like we did here. So, sorry, -2. -2. And then now you notice that this is also a common factor. Right? We have a common factor of x minus 2 in this whole thing. So then what happens is you factor out the x minus 2, and you're left with x minus 3. So for this one, this was actually a pretty simple example, right? We ended up with literally, again, just what we had here, just split up into these two pieces. So let's do one that's harder. I will say that this example here with a 2 in the front is one of my favorite to do because it trips up almost every single one of my students that I do it with. We'll do this one. Yeah, let's do this one, and then let's do a harder one. So I'm going to do, again, this is pretty much the same problem, so bear with me. It's going to be y equals, and again, you don't even have to have a y equals here. It can just be the expression part, which is just the stuff with the x's. So we could do that. But we'll go 2x squared minus 5x plus 3. Okay, a times c is still 6. We still get 1 and 6, 2 and 3 as our possibilities. We still have a larger number, which is negative, and we still have a product which is positive, so that means that it has the lower one has the same sign, so it's still negative. The only one that adds up to -5 is still -2 and -3, right? Everything's the same. But now when we split the middle term, this is a 2x squared minus 2x minus 3x plus 3. This changes what we factor. So in the first group and in the second group, now we have two different things. In the first group, our common factor is a 2x. And we're left with x minus 1. In the second group, we have a -3 that we can pull out, and an x minus 1 that's left over. If at this point you don't have the same thing in the parentheses, you've done something wrong. So it's pretty clear when things go wrong with this particular method. So this is usually called AC method. Oops. And I like it tremendously because once you generalize this, it works for every possible factorable trinomial. And it doesn't even have to be exactly a quadratic. it could be something that is in what we call quadratic form. So I'll show you another one after, after we do the harder example. All right, so here, x minus 1 is the common factor. Pull out x minus 1, and we're left with 2x minus 3. Woo! So this is the factored form of that quadratic here. So when I learned this, there was a lot of guess and check, and I hated it because it was just like, okay, well, we're going to split the first term into 1 and 2. So that means that, you know, m and n are going to be 1, 2 in some order. And then once you draw them in, then you say that the factor of 3 is going to be your p and your q, and then we'll try them in this order, and if it doesn't work, switch them and make sure it works in that order. And I was just like, I hate this, because especially when you start doing bigger numbers and they have more factors, it's such a pain. I didn't learn this method until I started teaching. And I was like, where's this been all my life? So let's do something that is crazy. Let's do 8x squared minus oh sure, let's go this way. Minus 27. And how many x's do we have in the middle? Let's make this positive. And $50. Okay, so 8x squared plus 50x minus 27. All right, now, you could possibly guess what the factors are going to be that make all this work, but it's a little inconvenient. So the way to do this one, again, just the same as what we did with the others, but what we're looking at is now 8 times 27 to get us the AC value. So A times C here, again, 8 times 27, it's going to be 160. This is 216. Maybe I shouldn't have done one that was so nice. So 216 is 6 cubed. And we've got 8 is all 2's, and 27 is all 3's. So again, I should have maybe thought about that a little heavier, a little more first, but it's fine. So taking 216, we can come up with a number of different ways for this to work. So again, 1 and 216, 2 and 108, 3 and 72. And again, you can come up with all the different values if you really want to. Or you can also make a couple of educated guesses as far as whereabouts this should be. Looking at 50 and knowing, without even completing the list, we know that, again, the bigger number, because A is positive, the bigger number, because of B, is also going to be positive. Bigger numbers are all going to be positive. And from C, again, since A is positive and C is negative, we're going to have opposite signs between them. So this is going to be -1, -2, -3, etc., all the way down the list, with positives in the larger position. So at this point, we know that we're going to be subtracting these two numbers. And we know that their difference is 50. So if at some point you come on here and you say, okay, I've got, let's do 6, and the number to get up to 216 is going to be 36. Okay, if you subtract these, you get 30. If you subtract these two up here, you get a 69. 69 is bigger than 50. 30 is smaller than 50, which means that the correct answer is between those two. This is like a number sense thing. It's not actually like the way to solve it, but it's just something to look at and be like, I think I know where this is. So as long as you keep getting numbers that are higher than this particular value, you need to make your numbers closer together. Excuse me one second here. Sorry. It's one of the problems with facial hair. Okay. So all of these numbers up here are too far apart from each other, and the number that you get for B is too big for what we are trying to get. The numbers all down here are too close together. So even if they're both the same sign, you're going to get numbers that are smaller than if you were way up here. This is also a thing later on if you're trying to find the the area of a rectangle that gets you the largest area when you multiply them together. That's maybe a bad idea. Largest area when you multiply them together. The optimal area for this is going to be a square. So that's what's gets you the maximum area is when the two side lengths end up being equal. In this case, it's sort of backwards because we're saying that the area is going to be constant. We just have different dimensions of fences. So the one that gives you the minimal perimeter is also a square. So again, you try to get stuff that's closer together if you want your sum to be smaller. If you want your sum to be bigger, then the sides of these rectangles need to be further apart from each other. Okay, anyway, that's enough of a diversion. So let's get to the point, right? Between 3 and 6, there's only one other number. It's 4. And with this, you can actually transfer where 2's are versus where 3's are. So 8 is 2, 2, and 2. 27 is 3, 3, and 3. You could choose where to put the 2's and 3's. So if we do like just these two 2's together, that gets us the 4. And then multiply everything else together. That's 27 times 2 is going to be 54. But if you want to get like the rest of the combinations, this is what you're doing. You're going to multiply together every different possible combination of 2's and 3's in order to, and again, change the order, associate them with each other. Every possible combination will get you every possible combination of factor pairs. Again, we could do all sorts of stuff here. So 8, negative 8, and positive 27 is where we came from. Sorry, the signs are backward, but 8 and 27 is where we came from, and then we can keep going from there. So there's 12 in here, 9, a bunch of other stuff. Anyway, when we look at this, again, we're going to see that negative 4 and positive 54 are the only two that add up to 50. So split the middle term again. 8x squared minus 4x plus 54x minus 27. We're going to associate the first two and the last two again, and then do group factor. So here we have between them, common factor of 8 and 4 is going to be 4. Common factor of x squared and x is x. And then we're left with, if we take 4x out of 8x squared, we're going to be left with 2x. Remember that what we're doing here is basically the reverse of distribution. So we're saying, like, what if we distributed it would get us 8x squared minus 4x. So 4x times 2x minus 1. Okay, bring down the positive again, and we're going to factor out a positive, in this case, 27, right? We know that 27 is a factor of 54. We did all that up here. So factor out 27 and multiply then. This is going to be 2x minus 1. Then this makes, no, I did it backwards. All right, factor out 2x minus 1, and it's leaving behind 4x plus 27. Now, I hope you're still here, and I didn't scare you off. Again, way to check it, best way to check it, multiply everything out as your particular distribution method. If you prefer FOIL, if you prefer the little Punnett squares that I make up here, that's an option. Or you could do the reverse and just distribute one of these things to each of the pieces on the inside of the other. You'll likely get nice numbers if what? So, Stwix, I really hope I didn't lose you here. Or if I did, please speak up. Yeah, I mean, the thing is that in my pre-calc class, right, I say, here's a quadratic. Have fun. You know, what are the x-intercepts of this thing? Go. And I don't give them any direction in terms of which method to use. Okay. I'm glad to see you're still here. Yeah, no problem, Strix. So the only other thing that I did want to get into, you know, without making it too much of a fuss, is what happens if this is something else. So I'm going to use, again, same numbers and different middle number. So if this was like 8x squared plus, let's go with, I blocked the, there we go. 6x minus 27. Sorry, 6x, hang on. Let me be crazy, because this also works. Oops. Okay, 8x to the 4th plus 6x squared y to the 3rd, because why not? Minus 27 y to the 6th. All right, this is insane. Your teacher probably won't give this to you. However, this is also of a quadratic form. How do I know that? Well, if we broke this up and we said let our for completeness, if our x's were instead of x squared and x and a constant, if our x's were then like, I'm being a horrible person, I'm sorry. If we let x squared be like u, then what we have is 8u squared plus 6u y to the 3rd minus 27 y to the 6th. Well, notice that now the u is quadratic. So in terms of u, we have a squared term, a linear term, and a constant term. in terms of the y's, we could also let y cubed be equal to v. So then we have an 8u squared plus 6uv minus 27v squared. Well, now notice we've got a quadratic going the other way. So you could also do this in terms of a quadratic using these. And again, like I said before, it doesn't matter. Like, all of this is done exactly the same way as we did the AC method over here. We can look at the middle term and say we need a 6 from our factor pairs. And this was a -9, -12. -9 is 2 3's, and then if we multiply a 3 by 2 is 6 by 2, well, by 4 is 24. So positive 24 and -9 don't add up to 6. 12 is 2 2's and a 3, right? A 4 and a 3, which leaves behind a 2 and 2 3's, which is 9, times 2 is 18. So positive 18, -12. There you go. That's going to be our factor pair for this set. What does that mean for us? Well, then we can do 8u squared. Minus 12uv plus 18uv minus 27v squared. All right, now if this is too hard for you, I apologize, and you can go on your way and have a nice evening. But this now, we can associate the first two things and the last two things just as we did before. So even if this problem looks way more complicated, it doesn't really matter. It's the same problem. Here, we take a 4 as the common factor between 8 and 12, and u between u squared and u, which leaves behind a 2u minus 3v plus common factor between 18 and 27 is a 9v, and we leave behind, again, 9 from 18 leaves 2, v from uv just leaves u, 9 from 27 leaves a -3, and v from v squared leaves a v. Again, they should have the same thing, and if you don't, you're in trouble. Factor out the common factor of 2u minus 3v, and take out, or what's left behind is the 4u plus 9v. Then you say, now let's plug in the stuff we had originally. All of our u's were just x squareds. So this is a 2x squared, and here a 4x squared plus minus 3 plus 9. And then the v was y cubed. So minus 3y cubed, and here plus 9y cubed. Now, did I even need to do the whole uv thing? No. You could have just left it as the original stuff here, done this broken up factorization with all of the x's and y's in place, and then eventually come out to the exact same thing. So, again, if that's too much for you, that's fine. I'm sorry, but this ends up working all the time. So if you can find something that has exponents that increase by the same amount every time, then you have something of quadratic form, and you can do this exact same thing. I will say, no matter what you're doing, always take out any common factors from the whole thing first. So we can see up top, right, 8, 6, and 27 don't have any common factors between all three of them. And then we don't have x's in the last term, and we don't have y's in the first term. So that's why we didn't pull anything out to begin with. But if there was like a y in the first term and some more y's elsewhere, then you want to factor out as many as you can. And same with numbers, and same with your x's. Okay, so Stuix, thanks for stopping by. If you have any more questions, let me know, and I can endeavor to not overwhelm you. Or if you're perfectly happy, you can look forward to more content like this. Yeah, I should probably apologize again because you said you were studying for your final, so you'd never do this. So, if your teacher did do that on the final, they're evil. All right, Superbrain. Any more criticism, feel free. All right. Um, yeah, so I really like. So I have not really particularly liked completing the square in terms of like going out and actually finding the C value. Um, saying, okay, I'm going to take half of that and then square it and then add that to both sides or whatever, split it out of the constant that we have. I don't really like doing that so much. But once I figured out that I could just find the vertex, I was like, oh, that's easy. So, I mean, if we go back to the original problem here, right, the 2x squared plus 15x minus 4, and did completing the square, again, the I really don't like it in terms of saying, see, the way we did it in school was we said this was going to be 2 factored out from x squared plus 15 over 2x plus c, or, well, it's not c, but whatever. The new value we need in here, minus 4 on the outside. And then we said here, it's, yeah, no, half of this one squared. So that's going to be 225 over 16. Ew. Scheitelpunkt. What does that literally translate to? So 225 over 16, I think, right? Because then this is going to be x plus 15 over 4. It's a point of apex. Okay, so then we added 225 over 16, which then we would have a minus 225 over 16 on the inside, which then we can take out by distribution, becomes a negative 225 over 8. Minus 4 is going to be a 32 over 8. So 257. Oh, right. Of course, it's 257 over 8 off of 15 fourths squared plus 2 on the outside like that. Right. So this little thing here was always my hang up. Like the factoring out and then getting this to the outside again. Just reminding myself, right, I can't actually do that. I need to have both pieces here, because otherwise it's not actually equal. There. Okay, much better. So yeah. So my hang up in high school was always taking these couple of steps to do this. And my professors, or my high school teachers, were like, oh, well, you just take like half this. You got to factor out the 2 first, and then you take half of what's here, and you square it, and that gets you the C value, or the yeah, Scheitelpunkt. And then you take that number and multiply it again, and then stick it on the other side. So this would be equal to 0, and then we'd actually take this over there, right? And this would be plus 225 over 8. And I was just like, why? Like, why would... This seems like a lot of work. So then, when I did this, I said, well, wait, this is vertex form. Find out where the vertex is. So, it's the same amount of work, if not slightly harder, but I just, for whatever reason, liked it more. So x is equal to, actually, let's back that up. It's not going to be x. The vertex is located at C, D in the form a times x minus c squared plus d, right? It's located at C, D. So c is equal to, this is our negative b. I'm going to do that again, aren't I? Negative b over 2a from the original capital A, capital B, capital C. Let's just avoid that problem. Right, so we take the original. Oh, right, I did h comma k was the See, this is why people did this. So if little c is this thing, then in this particular case that would have been negative 15 over 2 times 2. So negative 15 over 4. Right, and then d was equal to just plug the thing in. So d was equal to twice negative 15 over 4 squared plus 15 negative 15 over 4. So this is negative 225 over 4. This is going to be negative 225 over 8, or positive 225 over 8. Right, and that's another thing I like about that, where this is always half as much as that is when it's at the vertex. Just so perfect. So this is going to be a negative 225 over 8 minus 4, which we did up here. So we get a negative 257 over 8. That's equal to our d value. So like I said, it's sort of the same amount of work. It's just a matter of looking at this and saying, okay, this is equal to C, this is equal to D, and now let's plug it back into the transformation formula. So y equals A was 2, x minus negative is plus 15 fourths, all squared minus 257 over 8. So it's a matter of just what you like more. But I also found, like, trying to solve this, this is method 3. Right, so completing the square or vertex form. So 0 is equal to twice x plus 15/4 squared minus 257 over 8. Add it. 257 over 8 is equal to twice x plus 15/4 squared. Divide by 2 is 257 over 16. Is equal to that thing squared. Take the square root. Square root of 257 over the square root of 16 is 4 is equal to the absolute value of x plus 15/4. And now we use my patented method to figure this out. This is negative 15/4 here. The distance is the square root of 257 over 4 in both the positive and negative directions. So then we get our two solutions here and here, which again ends up being negative 15/4 minus square root of 257 over 4 and negative 15/4 plus square root of 257 over 4. Right. Right. In this particular method, I've shown this on stream many times, but yeah. So typically in America, we like keeping our constants to be integers, which again has its own benefits and faults and flaws and all that. But which calling them P and Q also has benefits because later on that crops up again in differential equations. Because when you have a second order differential equation, homogeneous in this case, but when you have a second order differential equation, you pop up with your P and your Q, which came from big P of x, y double prime plus big Q of x, y prime plus r of x, y equals 0. Yeah, I just realized that probably is a connection. That's probably where it came from, because that's the characteristic, and of course it would. Yeah. Huh. Because of course it is. Oh man, good times. Well, we made a new connection. That's good, or at least I made I made a new connection. You probably knew about that anyway. Um, All right, so I think, unless there are any more questions out there, we're probably going to wrap it up for the night. Yeah. It's just one of those random things that just is, of course, it's everywhere, but then you don't think about it. Yeah, I should start doing this with my students who actually are going up to differential equations eventually, and just start calling them P, Q, and R, and then P and Q. They'll yell at me, but still. All right. Well, I think we made some good progress tonight. On nothing in particular. Hmm. Okay, yeah. Because then you're looking at just what's these two in terms of constants. So let's see. Let's do it real fast then. All right, so that's going to be x equals negative b would have been Schwex. Thank you very much. I hope you enjoy your time here, but oh, I love those Bavarians. God, what's the next line? Oh, so meticulous. You quite possibly don't know that. Oh well. Let's be honest. You most likely don't know that song. Let's see. So B would have been Q. So Q over P would have been B over A plus or minus the square root of. This would have been B squared over A squared. Minus 4C over A. I think I've done this before. Over 2. So negative 4C over A is our... Negative 4. Okay. Yeah, I got it now. Yep. So this is your negative P plus or minus square root of P squared minus 4Q over 2, right? Okay, because you can factor out a 4 from both of those terms. Yeah, right. Okay. Right. So negative P over 2 plus or minus square root of P squared minus 4Q over 4. Yeah, all right. So I actually do highlight that. Yeah, okay, over 2 plus or minus. So I started highlighting this in my class. P over 2 parentheses squared minus Q. Yeah. So like this is an alternate way to get exactly the same thing as the quadratic formula, but we're doing it in terms of the vertex. So we do it in terms of C and D, or I guess A, C, and D, but still. So I take this thing, or I take the whatever. I take the y equals, sorry, 0 equals. Right, x minus c squared plus d. So I take this and then solve this one. So that's going to be negative d over a is equal to parentheses x minus c squared. Take the square root. Yeah. Take the square root of both sides. So that is the square root of negative d over a. Absolute value x minus c. That's plus or minus negative d over a, and then c. X. Yeah. I showed my students that one, and they're like, "Why haven't we learned this?" I'm like, I don't know. It's way easier if you know the vertex. All right. Well, thank you everybody for coming in. I'm gonna wrap it up and probably send everybody over to, let's see, Jason, I believe, is on tonight. Yes. Jason Charles Miller. So, send everybody over to Jason Charles Miller. He is a rocker musician type guy, and sings all sorts of really cool songs. Yeah, I just I typically like his stuff. I mean, not just like his music, but um, the streams he has are very chill, and everybody hangs out and has a good time. So go hang out with Jason tonight. Anyway, thank you for coming in. This is Obi-Wan Pez for N Simplex Pachinko. I will be back again on Friday for some games, and next Wednesday for more math stuff. Next Wednesday is my final exam day, so hopefully I'll have everything corrected and done by then. We'll see how it goes. What happened? Oh yeah, we're good. All right. See y'all later. Have fun. Be safe out there. Good night.